Suppose you are in a party room and you want to count the number of people. But strangely enough, the only method of counting that you know is counting years. So you start counting them. You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 years. So you write that down. 14 years. But since what you actually want to count is not number of years, but the number of people, you know that all you got to do is divide by 2. And by the way, let's assume for simplicity that everybody in the room has 2 years. So you divide by 2, and now you know that there are 7 people in the room. I admit that that is a somewhat bizarre example, but it is a valid example of the division rule. The division rule comes up when our method of counting counts each outcome more than once. If every outcome is counted the same number of times, we can correct the overcounting by dividing. Here, for example, we know that whenever we count 2 years, we are actually counting 1 person. So we can correct the outcome by dividing by 2. Getting a bit more mathematical, we can say that what we have here is a 2-1 function. And this can be generalized, of course. We can say that a k-1 function maps k elements of the domain to every element of the codomain. Now, what the division rule says is, if f from A to B is k-1, then the size of A equals k times the size of B. In our example, A is the set of years in the room, and B is the set of people in the room. And since this is a k-1 function, or more precisely a 2-to-1 function, we know that the size of years, so the size of A equals 2 times the size of people. Since what we want to know is the size of people, we can say that size of B equals size of A divided by 2, which is exactly what we did, right? We got the number of years and divided them by 2 to get the number of people. Now let's take a look at a less silly example. Suppose we want to count the number of ways to seat 4 students around a circular table. So we have students S1, S2, S3, and S4. If we apply the product rule, we might start by arranging them in order. We know that there are 4 factorial arrangements, so 24 linear arrangements. And when I say linear arrangement, I mean this would make sense if we had them arranged linearly, like S1, S2, S3, and S4. But at a round table, 2 arrangements that differ only by rotation are the same seating. For example, in our linear arrangement, if we had S4, S1, S2, and S3, this is a different arrangement than the first one. But in our round table, if we had S4, S1, S2, and S3, what we've done here was actually simply to rotate seats, which ends up being the same seating. Now the interesting question is, how many times is each distinct circular arrangement counted? Well, for any circular seating, we can rotate the seats 4 different ways. So we could have S3, S4, S1, S2, S2, S3, S4, and S1. And all these 4 arrangements in the circular table would actually be the same thing, the same seating. Which means that each circular arrangement has been counted 4 times in our 4 factorial result. Thus, by the division rule, the true number of distinct circular seating is 24 divided by 4, which is 6 arrangements.